Okay, so
Ok, ok. Você quer apresentar aí?
bom, você pode se você quiser, mas era só.
Tudo bem.
Okay.
Pode apresentar então.
Okay. So welcome everyone to this week's installment of the Brazilian Algebraic Geometry Seminar. Today we're very happy to have Javier Ribon from UFI, who will speak to us about local foliations with closed leaves. So Javier, please.
Thank you for the invitation. So first I'm going to make a very quick introduction. We're going to study holomorphic foliations whose leaves are analytic sets. I'm writing here essentially because, I'm going to explain later on, but the leaves are analytic sets. And the fundamental tool that we are going to use in order to understand these foliations is the holonomy group associated to a leaf of the foliation. Right? I'm going to remind everyone of the definition very quickly. So if you have a leaf of holomorphic foliation of dimension R, that means that the leaves are inverse manifolds of dimension R and codimension S, so the dimension of the ambient space is R plus S, okay? We can consider a submersion, okay, from a neighborhood of our leaf to the leaf, okay, such that, of course, the level sets of the submersion are going to be transverse to the leaf LP. Okay, it's a situation you're going to have, for instance, something like this. These are going, in this case, L could be the torus, and the level sets of pi are going to be these manifolds over here. If we are working, for instance, in dimension 2, the torus has complex dimension 1. These are going to be manifolds of dimension 1. Okay. And by using this, we can define the holonomy map along a path gamma. Okay, we're going to consider a path inside our leaf, a loop indeed. The initial and final point of the path are going to be the same, are going to be the point P. And given any point in the transverse, in the level set of the submersion through the point P, there exists a unique path contained in the leaf going through the point Q, such that the projection of pi is going to be gamma and the initial point is going to be Q. And we define the holonomy of the foliation along the path gamma at the point Q as gamma Q in 1. Okay, I understand that maybe this is, but if you have, for instance, you have, for instance, something like this, and you have here, that could be pi minus 1 of P, this could be P, this could be the leaf. Here we have the other fibers of the submersion, okay, and here we can have, for instance, gamma. What we are considering is a point Q, and we are just considering a path whose projection by P is gamma, and that is going to be something like this, right? And this point over here is going to be the image by the holonomy map along the path gamma at the point Q, because essentially the restriction of pi to every leaf is a covering map, roughly speaking. So that allows to make a continuous extension and to define these holonomy maps. This is let's say the concept that is analog to the Poincaré first return map, but since we are in the holomorphic case, the leaf is a manifold of real dimension higher than 1, so we have to be a little bit more precise, but it's essentially that. It's the Poincaré first return map. Okay, so we have this morphism we have a map that associates two loops at the point P. These local biholomorphisms defined in P minus 1 of P in a neighborhood of P. These maps are invertible because the maps associated to gamma and the inverse pet of gamma are inverse of each other. And what we can see is that this map does not depend on gamma exactly, but on the class that it defines on the fundamental group. And because of that, we have this morphism of groups. The image of this representation of the fundamental group is going to be called the holonomy group of the leaf L. Okay, and we are going to use that. We are going to relate the properties of having closed leaves for the foliation with the properties of orbits of the holonomy group of a leaf. Okay, an interesting theorem, okay, that it's let's say a foundational result is the Reeb local stability theorem. This is not a theorem for holomorphic foliations. You can consider just C1 foliations. And if you have a compact leaf and the holonomy group of the leaf is finite, is a finite group, then you have a neighborhood system of the leaf consisting of invariant sets. This is a fundamental system of saturated neighborhoods of L. Saturated means that it is invariant by the foliation, that it consists of leaves of the foliation. Okay, and indeed, you can go a little bit further. In this case, all leaves in a neighborhood of L are compact. So when we have finite holonomy group for a compact leaf and a C1 foliation, then all leaves in a neighborhood of our compact leaf are also compact. Okay, and it is easy to construct a first integral, so a function that it is constant on leaves defined in a neighborhood of L, because it's just considering functions that are invariant by the action of this finite holonomy group. And then you consider if in the case that here we had phi minus 1 of P, and we consider a function defined in this transversal that it is invariant by the action of the holonomy group, and then you extend it in the natural way to be defined in a neighborhood of the leaf, right? So when you have this stability in a neighborhood of a compact leaf, it is very, very easy to construct first integrals, holomorphic first integrals if we are in the holomorphic case. Okay, what we want is considering foliations with closed leaves in the holomorphic setting. But there is an issue with the complex analytic setting, and it is that in some cases, for some manifolds, all leaves have singularities. So for instance, if you have foliations in CP2, all of these foliations have singular points, and there are always leaves, for instance, by using Camacho's theorem, that are not closed. So in particular, if you consider as a definition that all leaves are closed, this definition could be empty for the case of CP2. So in order to consider a little bit more inclusive definition, we are going to say that F, the foliation, has closed leaves if the closure of the closure in the usual topology is an analytic variety of the same dimension as the dimension of the foliation. So L is going to be an immersed manifold of dimension P, and its closure is going to be an analytic variety of dimension P. For instance, with this definition, you can consider the radial foliation in C2 or CP2. The leaves of both these foliations are the lines through the origin, but you have to remove the origin, okay, because the origin is a singularity. It's the lines through the origin, but you have to remove this point. But if you consider the closure, the leaves are the closure of any leaves line through the origin, so it's closed. Okay, so in this way, we can, for instance, consider this example. There are some natural questions. It is clear that if you have a stability means that the conclusion of the Reeb local stability theorem holds. Okay, so that you have a system of a neighborhood system of the leaf consisting of invariant sets. Okay, and it's clear that if you have stability, at least when we are working in a neighborhood of a compact leaf, this implies that all the leaves in the neighborhood are closed because they are all compact. So this implication over here works very well. But the other one, is it true, or is it true in some cases that if you have closed leaves, you have stability, you have finite holonomy groups? We are going to consider that. And another question is, in the case of having finite holonomy groups, do we have first integrals? We said already that that's true for the case of regular foliations and the neighborhood of a compact leaf, but the question arises for singular foliations. Okay, and the answer for both these questions is no. It's not true that closed leaves implies in general stability, and it's not true that stability implies existence of first integrals. It's true under certain hypotheses that I'm going to comment later on. So the first question, closed leaves does not imply stability. And we are going to introduce an example, okay? We consider this should be the torus here, okay? Torus T2, right? And we consider the torus as the quotient of the complex plane by the group of the transformations of the torus. And we are going to consider a rank 2 vector bundle over the torus, which is going to be given by this equivalence relation defined in C3. In the torus, we have to identify C with C+1 and C with C plus I. But we are going to extend the identification by identifying CXY. C is in C, X is also in C, and Y is also in C, with C+1, X, and X plus Y. And here we are going to make a simpler identification. We identify CXI with C plus I XY. In this way, this quotient over here is going to be a rank 2 vector bundle over the torus. And there exists a natural foliation. This is an example of a suspension. And there is a natural foliation, which is the horizontal one, in which the leaves are the images by the projection from C3 to the quotient of sets of the form C times a point in C2, because the deck transformations of this space actually, or if you want to, okay, these transformations preserve the foliation. These two transformations indeed preserve the horizontal foliation. Okay, so what happens is that since this suspension, the properties of the foliation are going to can be indeed translated into the properties of the holonomy group. And the holonomy group, in this case, for this for the leaf, which is the zero section, okay, this holonomy group is generated by two biholomorphisms. The first one is the identity map. It's this one over here. This is the identity map, sorry. And the second one is a linear map that sends xy to x plus y, which is here. And the property of having closed leaves for this suspension in the neighborhood of the zero section is equivalent to the property for this group to have finite orbits in the neighborhood of 0. This is not going to be a problem. And this map over here has finite orbits in a neighborhood of 0. It does not have finite orbits, of course, in C2, but it does in a neighborhood of 0. We're working here in the local case because we have this situation. And when you fix x equal x0, the restriction of f to this line is a translation. Well, it's a translation if x0 is different than 0. It's a non-trivial translation in that case. And translations have finite orbits in bounded domains. And in the case in which x0 is 0, then it's even simpler because all points are fixed, so the orbit of every point is itself. So all orbits are finite, and because of that, we have that leaves are closed in the neighborhood of the 0 section. So we have closed leaves, but we do not have stability. Okay. Another question is whether stability, this property of the leaves having finite holonomy groups, implies that there exist first integrals, let's say meromorphic first integrals, integrals that are quotient of holomorphic functions. And the answer is also no. And there is a very well-known example by Suzuki, which is an example like this. If you you have, I don't know, I know this, you have a situation that I don't know very well in a neighborhood of the origin of C2, and then you can blow up the origin, and you're going to obtain here a CP1, which is the preimage of the origin by the blow up. And what happens is that one of the leaves, it is going to be tangent to this CP1, and the other ones are going to be transverse. We are going to have something like this. And the properties of the foliation in the neighborhood of this point somehow forbid, let's say, this foliation from having a meromorphic first integral. Okay,
Javier,
I'm not going.
Sorry, but I think that the equation of Suzuki's example is wrong. You just put Poincaré-Dulac singularity.
Sure, maybe it's maybe I took it from the paper from Suzuki. I didn't check, but okay, then forget about the equation. It's going to be something like this, and it's going to be a transcendental first integral, something. But I think it's something like in the paper that I saw, it was something like this. But okay, maybe the example is wrong. But you don't have a meromorphic first integral. Okay, so you don't have that. Stability implies existence of meromorphic first integrals, for instance. So let's see now a few positive cases. Okay, the first one in the local case. If you have a holomorphic foliation defined in a neighborhood of the origin in Cn that has codimension 1, so the leaves have dimension n-1, they are inverse manifolds of dimension n-1, and we suppose that all leaves are closed with the definition that we gave, in other words, that the closure is analytic, then if on top of that, we suppose that there are finitely many leaves whose closure contains the origin, then F has a holomorphic first integral. The Suzuki case, of course, does not satisfy this hypothesis because in the Suzuki case, there are infinitely many leaves whose closure contains the origin. Indeed, every leaf satisfies that its closure contains the origin. But if that set of leaves is finite, then F has a holomorphic first integral, okay? And this is a very celebrated result in the theory of complex of holomorphic foliations because it provides a topological criterion for the existence of holomorphic first integrals. If you have now a homomorphism that preserves the leaves of the foliation, that sends one into another, and it preserves the leaves, then since these conditions over here are topological, having closed leaves or the closure containing the origin, it's going to be preserved by homomorphisms. So if you have this situation, a local holomorphic foliation of codimension 1, you have that the property of having a holomorphic first integral is indeed topological. It's of course, because this is indeed a if and only if. You have a holomorphic first integral that is non-trivial, then all leaves are closed, and there are finitely many leaves whose closure contains the origin. Okay, in the global case, you have this very beautiful paper by Edwards, Millet, and Sullivan from '77. That is a paper that is much more general than, let's say, the complex analytic setting. It studies foliations with much weaker regularity. And it studies foliations with compact leaves on compact manifolds. And there is a condition to guarantee that such foliation with closed leaves, in that case with compact leaves, is always stable. In the holomorphic setting, the simplest corollary of their theorem, a corollary that they present in the paper, is that if you have a regular holomorphic foliation with closed leaves defined in a Keller manifold, then the foliation is always stable, meaning that the holonomy group of every leaf is finite. Okay. This, as I said, does not use complex techniques at all. It's a more general result. By using, let's say, more techniques that are more oriented to algebraic geometry, we have this result by Gomez-Mon of '89, in which he shows that if you have a holomorphic foliation of dimension p that have closed leaves in a projective manifold, because he needs that that property, he needs to use the Hilbert scheme of manifolds of dimension n minus p. And if you suppose that the dimension of the singular set is less than p, then the foliation is stable. But it's not just that, it admits a non-trivial meromorphic first integral. Meromorphic first integral is not a constant. So we have these positive results for the global case. Here, Keller manifolds, in which we have stability, and here, projective manifolds, in which with this condition, we have stability and the existence of a meromorphic first integral. Okay. We can consider this problem too in the local setting. Okay. We can consider, for instance, this setting in the neighborhood of a compact leaf of a codimension Q holomorphic foliation, and trying to understand something. Okay, so if we have stability, or what we can say if we do not have stability when all the leaves are closed. So what we do have, for instance, when we are working with a compact leaf, is that the leaves of the foliation are closed in a neighborhood of this compact leaf, if and only if the holonomy group of this leaf has closed orbits. But it is very easy to see that having closed orbits and finite orbits are equivalent. This is a very simple exercise. So we have that closed leaves in a neighborhood of L is an equivalent condition to the holonomy group of L having finite orbits. Okay, it's a group that in this case is going to be finitely generated, and we want to find a neighborhood of, yeah, okay, I'm going to explain. So we are in a situation, for instance, if our leaf is a torus and we consider here transversal to this leaf, T, this T is going to be locally, okay, in the neighborhood of this point is going to be just, it's going to be essentially the same thing as the neighborhood of CQ at the origin. And what we have is that the group is, the holonomy group, as a consequence, can be interpreted as a subgroup of the group of diffeomorphisms defined in a neighborhood of 0 in CQ. Okay. More precisely, because, okay, I think I'm going to be a little bit more formal for a second. you consider this group over here, the group of local biholomorphisms defined in a neighborhood of 0 in Cn, which is the group of biholomorphisms phi from U to B, where U and B are open neighborhoods of the origin in Cn, okay, and 0 is a fixed point. And what happens is that you give yourself the right to reduce the domain of definition. That you consider an equivalence relation so that we are not considering a fixed domain of definition, but we can always reduce this domain of definition. Okay, in this case, of course, once you have one of these local biholomorphisms, you have to fix a domain of definition, and you can define in this way a positive and a negative orbit in some domain of definition U. So the positive orbit is the set of positive iterates in which we are assuming that all iterates till k are in U. So this allows to define phi to the k at P, and we require that all these iterates of P belong to U. In the same way, we can define the negative orbit just by replacing phi with its inverse map. So it's okay. And we can define the total orbit by considering the union of the positive and the negative orbit. Okay. It's the definition of the orbit, just we are fixing where the orbit has to be. It's just that. The definition is finite orbits is the following. We say that local biholomorphism has finite orbits if there exists a neighborhood U of the origin in Cn such that the orbit of the point P by phi in U is finite for any P in U. Of course, you can have biholomorphism of this kind such that it does not have finite orbits, but it can have finite orbits in a smaller domain. That's the reason we give ourselves the right to reduce the domain of definition. But once we do this, this is going to be a property of this germ of biholomorphism, because once it's true for some U, it is true also for any open set contained in U. So we can define this finite orbits property. Here it's not, we say that, okay, definition is the definition of when phi has finite orbits. We say that phi has finite orbits if there exists a neighborhood, should be here. If there exists a neighborhood U of 0 such that the orbit is finite for any P in U. Okay, this theorem, we already talked a little bit about it, is the Mathematic theorem, the topological criterion for the existence of first integrals. Okay, and what happens in this case, and the reason why the codimension 1 hypothesis is very important, one of the reasons, the most important reason, I think, is that if you consider a finitely generated subgroup of the group of local biholomorphisms in one complex variable that has finite orbits, then G is always finite. So, and this, as we said, when this group, when the holonomy group is finite, it is it's possible. It is not hopeless at all. It's possible to. It is at least likely to find first integrals. So the point is that for groups of local biholomorphisms in one variable, finite orbits implies stability, implies finiteness of the whole group, right? In the example that we gave of a foliation that has closed leaves, but it's not stable, we consider suspension. Here we have two biholomorphisms in C2. They are both linear. We are considering them just in a neighborhood of the origin. And of course, this one has finite orbits, the identity. And this one has also finite orbits in a neighborhood of the origin. So we can use examples of local biholomorphisms that have finite orbits but are not of finite order to find examples of foliations that have closed leaves but have no finite holonomy groups. Okay. Okay. Something I forgot to say that at the beginning, all these results are joint, but indeed most of them are part of the PhD thesis of Lucivânio Lisboa. Who was my PhD student. And there are other results that we obtain later on. Okay. Something that it is interesting is if we consider one of these local biholomorphisms, in the linear case, then this phi has finite orbits. Again, it's finite orbits in a neighborhood of the origin. It's not a finite orbits in the whole Cn, even if phi, if it's linear, it's defined in the whole Cn. But then it has finite orbits. That's very easy to show if the spectrum of phi, indeed this should be the spectrum of the linear, but in this case it's linear. So the spectrum of phi, sorry, consists of roots of unity. Okay, that does not imply that it has finite orbits in Cn, but it implies that it has finite orbits in a neighborhood of the origin. Right. So the problem that we are interested in is to relate the property of finite orbits for a local biholomorphism and for its linear part. Because if you, for instance, have studied at some point the theory of local biholomorphisms in one complex variables, classifying, for instance, topologically or analytically, these objects is absolutely hopeless because there is many of these local biholomorphisms in which you can find chaos. It's a phenomenon called small denominators. Okay. So you cannot classify, for instance, local biholomorphisms in one variable up to analytic or topological conjugacy, but you can try at least to understand in which conditions this phi is analytically conjugated to its linear part, or topologically, or and this is a problem that it is much more easy to deal with. It's not easy at all, but it is easier than the previous one. And what happens is that, for instance, for many linear parts, you're gonna, of course, if the linear part is hyperbolic, this is always true in the analytic setting. But even if the linear part is not hyperbolic, you're gonna have many cases in which certain linear parts imply, if you have certain linear parts, you have conjugacy, analytic conjugacy of the diffeomorphism and its linear part. Yeah, and this is let's say what we can say, because to describe completely the dynamics of these objects is something that it is brutally hard. Okay. So we want to know what's the connection between the finite orbits property for phi and the finite orbits property for the linear part of phi at 0, for the Jacobian matrix of phi at 0, if you prefer. What happens is that all eigenvalues of this linear part are complex numbers of modulus 1. And this is a consequence of the stable manifold theorem. For instance, if you have lambda, which is an eigenvalue of the linear part of phi, and let's say that the modulus of lambda is smaller than 1, you can find a stable manifold. So you're going to have some submanifold of Cn. Here we have the origin, in which the dynamics is attracting. Okay, all the stable manifold is going to be the basin of attraction. It's going to be a basin of attraction of 0. And in particular, that implies that you don't have finite orbits, because the orbit of every point in here is clearly infinite. So you cannot have eigenvalues of modulus less than 1. Of course, you cannot have eigenvalues of modulus bigger than 1, because you can make the same argument for the inverse of phi. So all eigenvalues have modulus 1. This is just the stable manifold theorem. Okay, so we know that. We are interested in understanding this difference between having finite orbits and having finite order. We know already that there are examples of local biholomorphisms that have finite orbits in a neighborhood of 0, but they do not have finite order. I'll remind you of this example. It does not have finite order, okay? Because if you consider the kth iterate is going to be x kx plus y. So if k is different than 0, this is not the identity, so it does not have finite orbit, but it has finite orbits. And we want to see what there is in the difference of these two sets. Okay, so we have this result. At the beginning, we didn't know very well what kind of examples we can find. You have the example that I wrote of, as I said, local biholomorphism with finite orbits, but that does not have finite order. But if you see this example, for instance, both eigenvalues are equal to 1. This is an unipotent linear map. And the issue is that, of course, you can consider somehow a finite covering, and in that way, you can transform these eigenvalues into roots of unity. But an interesting question is whether all the examples are like this, whether all the examples are of examples in which the linear part has the finite orbits property, because for linear maps, the finite orbits property is equivalent to all eigenvalues being roots of unity. Okay, and we try to find new examples. And the first thing that you try to do is considering the simpler situations. So we consider a local biholomorphism that is embedded in a one-parameter group. So essentially, you have a complex analytic vector field defined in a neighborhood of the origin in Cn, and you consider its time t map. Okay. So this time t map is gonna be a discrete dynamical system, which is somehow it comes from a continuous dynamical system. And in this case, you can prove that all eigenvalues, if phi has finite orbits, all eigenvalues are roots of unity. So you do not find more examples than the one that already existed previously in the literature. Okay, you have examples in which the linear part also has finite orbits. So you have to go further than that. You have to try things that are not embedded in one-parameter groups. Okay, so it's just what I said. In the continuous case, continuous here means that phi is embedded into the flow of a vector field, so a continuous dynamical system. If phi has finite orbits, then since all eigenvalues are roots of unity, the linear part of the origin also has finite orbits. So this implication, finite orbits for phi implies finite orbits for the linear part, could be true so far, but it's not true. what happens is, if you consider a Kramer number, I'm going to give a definition in a minute, you always have a holomorphic function defined in a neighborhood of the origin in C. This condition means just that it's a function defined in a neighborhood of the origin in C such that the image of the origin is 0. And you can consider this diffeomorphism over here. Indeed, in the examples, we find examples in which A is an entire function. So you consider this, if A is an entire function, this is a diffeomorphism of C2. And you can find some A such that this diffeomorphism has finite orbits in C times U for any bounded neighborhood U of 0. Okay. In particular, for any bounded neighborhood of 0 in C2. So what is a Kramer number? Kramer number is going to be lambda, which is not a root of unity and has modulus equal to 1. And besides that, that satisfies this condition, which is essentially being very, very, very well approximated by roots of unity. If you have a root of unity, this thing over here is for some n equal to 0. But what happens is that this is not 0, but even if we consider the square root, which is going to make this quantity much bigger, even then the lim of this sequence over here is going to be 0. So lambda is very well approximated by roots of unity. And in that condition, we can always find an A of this form such that this diffeomorphism over here has finite orbits. And obviously, since lambda is not a root of unity, it's not a finite orbit. So I'm not going to give the proof, of course, but because it's essentially doing some calculations, what you have is that if you write A as you consider the Taylor power series expansion of A at the origin, the nth iterate of phi can be written in that way. And what you have always is that for every x, here you have a rotation in the variable x, but once you fix x, you have here a translation. And what you want is this quantity to be big. And you get that by making these denominators very close to 0. But okay, this is just an idea. Okay, I'm going to talk a little bit about this case because I think it's interesting. And in order to do so, to give some context, I'm going to talk about the Euler example. It's not because this is related to the Euler example, but it is because it's a similar phenomenon. If you have here this vector field, you have two formal invariant curves. Okay. One of them is x equals 0, is the y-axis, and the other one is this curve over here. How do you find this curve? You consider something like this, and you write down the equation that is satisfied by an invariant curve. If we call this vector field x, the equation is that this function over here divides the result of applying x to the same equation. Okay, we are working in the ring of formal power series. If this happens and this series over here converge, then this is the equation of an invariant curve. Essentially, we are saying that this condition implies that the vector field x is tangent to the 0 set of this function, and so that the 0 set of this function is invariant. But you can actually try to consider this condition when this series over here is any series, even a divergent one. And in that way, you are going to obtain a recurrence equation for these coefficients. every coefficient is going to depend of the previous one. And so by using undeterminate coefficients, you obtain that this thing, at least formally, is an invariant curve of this vector field. Okay, so since this is divergent, apparently it means nothing. Okay, but we have this picture over here. This is a picture for R2. In C2, the situation is a little bit more complicated, so I'm going to stay in R2 for this discussion. What happens here is that to the left of the y-axis, we are going to have one curve that it is invariant and goes to the origin. And this curve has a C-infinity expansion at the origin, which is exactly this one. So, of course, this does not converge. So this curve that we find over here is not analytic, but it is, let's say, a C-infinity curve. Okay, sorry, it's a C-infinity curve whose Taylor power expansion at the origin is, if you want, this can be written as a graph. And what we are saying is that this function over here is C-infinity, and its expansion at the origin is exactly this one. And to the right of the y-axis, the situation is even better because we have infinitely many of these invariant curves that go to the origin, and all of them satisfy the same property. They're all C-infinity, and the Taylor expansion at the origin is this one. So we have, of course, none of these curves is analytic, but we have a geometric realization of some kind of this formal object that's invariant by the vector field. Okay. What happens in our case, when we consider a local biholomorphism that has, of this kind, that has finite orbits, is that, okay, there are two formal invariant curves. One of them is the y-axis, is x equals 0. That's the fixed point set of phi. Okay, if you consider the fixed points of phi are all the points such that x is equal to 0. But you can use undeterminate coefficients again, and you are going to find a unique curve of this kind. Indeed, there are the two unique formal invariant curves that are invariant by phi. What happens is that this curve over here has to be divergent, meaning that B has to be a divergent power series. Because, sorry, we have here x equals 0. Here we have, let's say, I'm writing here in this way because it's not a real curve. But if this curve were analytic, what you could have is that the multiplicator of the restriction of phi to the curve at the origin would be equal to lambda. And we could obtain a finite orbits diffeomorphism in dimension 1. And in dimension 1, finite orbits implies it's equivalent to being periodic. So lambda in particular would be a root of unity, which is not the case. So this curve over here is divergent. And indeed, you can find for every point in the fixed point set, you can find passing through every point a divergent curve. But these curves cannot be realized geometrically. That's more or less the idea, because if you have a complex, if you have a local biholomorphism in dimension 1, whose multiplicator is lambda, here we have the origin, you're always going to have some, I don't know, you're going to have some compact, you're going to have an invariant continuum, an invariant non-trivial continuum, such that the unique periodic orbit in that continuum is the orbit of the origin. And obviously, we're not going to have this kind of thing over here because orbits go away. So there is no way of realizing this invariant curve in a geometric way, because all orbits except the orbits of the fixed point set go away. They escape from the domain of definition for both the positive and the negative iteration. So we obtain in this way things that are not easy to realize. And indeed, if you consider the problem of realizing geometrically invariant curves, formal invariant curves for local biholomorphisms, this is the unique case in which you don't have some kind of geometric realization. The case in which the multiplicator is of modulus 1, but it's not a root of unity. If the multiplicator is hyperbolic, or if or I don't know, if it's a root of unity, you have always some kind of geometric realization. Okay, so we obtain here, let's say, a foliation, a divergent foliation, if you want, in which all leaves are difficult to interpret from a geometric point of view. Okay, so what
Are you saying that these leaves are not Gevrey? So the divergence is wild in contrast with the Euler example?
I don't know. I don't know. I didn't check if it's Gevrey. That's a good question. I don't know. I think it's easy to check out. I suppose, I don't know, but I think that you can find examples that are Gevrey. But because you can prescribe pretty much. Sorry. You can prescribe more or less how fast the coefficients of this A increase. But so yes, I think that you can find some Gevrey things, but I don't think that all of them are Gevrey. I think that you can, but I don't know, I can check it out. I think that you can find examples of both kinds. Okay, here we are. So we saw in the previous slide an example of a diffeomorphism in dimension 2 that has finite orbits, and such that it has one eigenvalue which is equal to 1, and another one which is of modulus 1, but it's not a root of unity. I have to, this diffeomorphism is of this kind. So the linear part is this one, so the eigenvalues are lambda and 1. So it's not true. What we want to see is if finite orbits for phi implies finite orbits for the linear part. That's not true, okay? Because we have examples in which one of the eigenvalues is not a root of unity. But we find always examples in this way in which one of the eigenvalues is a root of unity. Indeed, in this example, exactly equal to 1. So what we can say is this a general situation, or it's just that we are not considering the right examples? And this theorem says that this theorem is proving the thesis for dimension 2, but it can be generalized to any dimension. It says that if you have a local biholomorphism with finite orbits, then for some iterate of phi, then the origin is not an isolated fixed point. Okay? So in particular, if you consider this equation over here, the spectrum of the differential of, the spectrum of the differential at the origin of phi to the k minus identity, this thing has to contain 0, because otherwise you can use the inverse function theorem, and this equation equal to 0, which is the equation of the fixed point set, has just one solution, which is the origin. So we have that, but this implies in particular that one is going to be an element of the spectrum of the differential of phi to the k at the origin, and this implies in particular that the differential of phi at the origin contains a root of unity. So this theorem over here guarantees that finite orbits implies that at least one of the eigenvalues of the linear part is a root of unity. Okay. It's a sort of Camacho-Sad theorem for the finite orbits case. You're finding an object, for instance, if you're in dimension 2, you are finding a curve that it is invariant by phi, and it is analytic. It's not formal or anything like that, and it works in any dimension. If you consider the Camacho-Sad theorem, for a while there was a question if this theorem was true for vector fields in dimension 3. If you have a vector field, holomorphic vector field in dimension 3, is there always an invariant curve going through the origin? And the answer is no. There are examples of Gomez-Mon and Luengo that they give example of X with no invariant curves through the origin. Of course, under this hypothesis, which is kind of restrictive, we always have these invariant sets for every dimension. Okay. And as I said, as a corollary, we have that if phi has finite orbits, at least one of the eigenvalues of the linear part is a root of unity. So we have this property, and I gave the example for dimension 2, but you have examples of diffeomorphisms with finite orbits for every dimension, such that the spectrum contains exactly a root of unity eigenvalue, counting multiplicities. So what we know is that the examples that we find are sharp. We do not have that finite orbits for phi implies the same property for the linear part, because it's not true that all eigenvalues are root of unity, but we find something intermediate. We don't find also that it does not imply anything for the linear part, because the linear part has at least a root of unity eigenvalue. We find that we have at least one. So we have some kind of intermediate finite orbits property for the linear part of phi at the origin. Okay, how I'm going to give a very rough idea of the proof. What we do here, the way in which we study this is by considering the so-called bad set. So we consider a regular foliation, for instance, with compact leaves. I'm going to introduce the bad set for foliations, and I'm going to explain what the generalization is for groups of local diffeomorphisms. If this bad set, for instance, is defined in the paper by Edwards, Millet, and Sullivan. If you consider a regular foliation with compact leaves on a compact manifold, the bad set is the set of leaves in which the volume function is not locally bounded. So you have a volume function that is defined in the leaves. To every leaf, we associate its volume. And if this volume function is not locally bounded in the neighborhood of a given leaf, then this leaf belongs to the bad set. In our case, essentially, the bad set is the set of periodic orbits. Okay, so we want to study the structure of the set of periodic orbits. And we have here some properties that I don't have the time to explain with more detail, but something that you have in this case is that the set of periodic orbits contains a non-trivial continuum containing the origin. That's not a difficult thing to prove. It's essentially a union of analytic sets, because if you have periodic, a periodic point is contained in, it's always in the fixed point set of some iterate, and these sets are analytics. So B is somehow a countable union of analytic sets. And what happens is if we have some irreducible component of this one fixed point sets of some of the iterates, this map that sends P to its spectrum is constant in gamma. And so if we have here a gamma, which is contained in the fixed point set of some iterate, here it should be K, of course. What happens is that this map sends P to the spectrum, but the spectrum never contains eigenvalues of modulus different than 1 by the stable manifold theorem. So you have essentially here a holomorphic function, or several holomorphic functions, because the dimension is n, such that they never take values outside of the circle, so they are constant. This is essentially the proof. So eigenvalues in these irreducible components of fixed point sets are indeed constant. The spectrum is constant along these components gamma of the fixed point set of iterates. And we have that a chain of irreducible components. I'm going to, I don't know if I have to, I can explain. A chain of irreducible components of sets of this form is finite. Okay, okay, very, what we're going to use our result. This is the most important part of the proof. The other are more or less automatic. To prove that a chain of irreducible components is finite. I didn't define what that chain is, okay, but I'm going to define. You consider a diffeomorphism. We're going to use this lemma, which is going to be fundamental to prove that a chain is finite, whatever that a chain is. You consider a local biholomorphism whose spectrum contains just 1. And you consider a germ of analytic curve at the origin. So if gamma is periodic by phi, it's invariant. That happens always when the linear part has just the eigenvalue equal, the eigenvalue 1. And if gamma consists of periodic points, then it consists of fixed points. So this property on the linear part makes things that are periodic, things that are fixed, which is a very nice property to have. What it is a chain? What we can do is we consider a sequence of irreducible components of fixed points of some iterates of phi, okay? And a chain is one of these sets in which, okay, it's like this. It's a sequence of curves of this form in which every curve intersects the next one. So gamma 1 here is contained in the fixed point set of the Kate 1 iterate, gamma 2 in this other fixed point set. K1 and K2 can be different, but it's obvious that the union is contained in the fixed point set of this iterate, in which the iteration, the number of times we iterate is the product of K1 and K2. What happens is that it is very easy to prove in this case that the spectrum of the linear part at this point contains just the eigenvalue 1. Okay? And all these points are fixed by this iterate over here. So when we get to this point, since the spectrum is constant along this line, it's going to be a singleton whose unique element is 1 also at this point. This is what it is written in here. And now this blue curve over here is not necessarily an invariant curve of this local biholomorphism, but it is a curve that it is invariant by some iterate. So by using that the spectrum is equal to 1, where it is periodic, it becomes invariant. So this is an invariant curve by this iterate of phi. And indeed, all the points in here are periodic. But where it is periodic becomes fixed. So it is a curve of fixed points of this iterate. And you can keep going. So at the end of the day, a chain is going to be contained in the fixed point set of some iterate. And as a consequence, a chain has a finite number of irreducible components because this set has a finite number of irreducible components. So chains are disjoint and compact. The path set is a disjoint union of chains. The connected component of the origin of the path set is a disjoint union of chains too. And these chains, since they are finite, they are compact. And if you have a continuum that is a countable union of pairwise disjoint compact sets, then at most one of them is non-empty. This theorem is due to Sierpinski. Okay, so that means that, the connected component of the origin of the bad set is indeed a chain. So it's an analytic set. And in particular, since it's a non-trivial continuum, it has to contain an analytic curve through the origin. So that's the proof. So that's what we prove. The connected components of the bad set are analytic. The bad set is not analytic because it can be a countable union of analytic disjoint sets, but the connected components are analytic. And finally, this result can be generalized to higher dimension. In this case, we are going to have an analytic manifold through the origin of positive dimension consisting of periodic points. And you can even generalize it for groups. And as a consequence, we can go back to the initial problem. If you consider a codimension P, regular holomorphic foliation defined in a neighborhood of a compact leaf L, and you assume that the foliation has closed leaves in a neighborhood of L, then there exists an analytic set of dimension greater than n minus p. N minus p is the dimension of L. So of dimension higher than the dimension of the foliation, such that this analytic set is invariant by the foliation and contains L, and there exists a neighborhood system of neighborhoods of L in S that are invariant by the foliation, that are saturated. So by Reeb stability theorem, they consist of compact leaves. So you get into the situation of Reeb stability theorem for intermediate dimension. I mean, you have a leaf L whose dimension is n minus p. Of course, you have there something that is, the leaf is compact, invariant, and has dimension n minus p. But you have something that is also invariant, and it's a union of compact leaves in dimension higher than n minus p. It doesn't get to be dimension n. So you don't get to have a stability, let's say, in a neighborhood of L, but you get a stability in intermediate dimension. You get the situation of the Reeb stability theorem for intermediate dimension. That's the main result. So thank you very much.
So please unmute yourselves and let's thank Javier for his beautiful talk. And yeah, questions for Javier.
So I have a comment. Indeed, this last result in the projective case, you can make it quite stronger, right? Because since this guy is invariant and contains L and saturated by algebraic subvarieties, either it's Zariski dense, and then you can propagate this, you get to the actual Reeb stability, or this will be algebraic. So you get algebraicity of this S in the algebraic situation.
Yeah. Yeah, I'm going to check that out. Yeah. Sure. If you impose further properties, you're gonna get a much stronger results. Yeah, that's very interesting.
But that's very nice, huh? Very, very nice.
Yeah. I don't know, at the end of the day, for instance, I don't know, it's interesting to see what you can say without considering holomorphic things. I mean, for instance, in this paper by Edwards, Millet, and Sullivan, they prove plenty of things without considering at any point anything holomorphic. But yeah, here what we have in the holomorphic case is that it is easy to prove that this bad set has a very nice structure. And then with that structure, you prove all the other results. All the other results are consequences of the description of the bad set.
Mm-hmm.
I just have a very naive question. I mean, which is,
Sure.
so are there sort of natural directions, questions to ask related to the moduli space of foliations? I mean, they go farther along this line. I mean, or either you could describe, I don't know, locally inside the moduli space of foliations that have, I don't know, foliations that are near a given foliation with closed leaves in a neighborhood of a leaf or something like that. I mean,
I think you can try to consider that kind of problem because, for instance, this example that I gave at some point, an example of, I don't know where it is, but more or less, yeah, an example of a diffeomorphism that has finite orbits and it has no finite order. What happens is that all the examples that have that property, that the linear part, okay, what we want is diffeomorphisms that have finite orbits, but they do not have all the eigenvalues being roots of unity. And what happens is that all these examples have common properties. I mean, you can characterize several properties of this example. So I think that you can try to classify them because, as I said, they have common properties, but I'm not sure exactly what the classification would be. But yeah, it can be tried. It can be considered for sure. Because, as I said, there are all the examples are in, let's say, in a family, in a very particular family. All of them have this property that I said. This property that I said that you have a fixed point set that it is indeed smooth, and then you have a foliation by an invariant foliation in which foliation, okay, it's not a foliation because these things are analytic, but you get the point. You have a foliation, let's say, in which all leaves are divergent. This property is shared by all the examples. So I think that, yeah, you can try to classify them. You can try to see, let's say, how to deform them, things like that.
any further questions for Javier? So if not, thank you again so much for your talk, and thanks to all of you for coming out to the seminar today. And we hope to see you next week.
Thank you. I'm going to